Today we're going to review some of the things that I did on Desmos in class today, and that would be some reviewing of square root basics. Now, know that there's a document on our Google Classroom called Square Root Basics, and it goes through all of the things that I'm about to go over, but it's nice to go over it and see what's happening. So I'm going to demonstrate a problem, and then I'm going to give you a problem similar to it. I suggest you pause the video between so you can try the problem. Square root of 64 is 8 because 8 squared is 64. 8 squared is 64. Therefore, these are opposite things from one another. 8 squared is 64. Square root of 64 is 8. So other perfect squares would be something like 25 or 49 or 100. Just take a second. Make sure you know those. Pause if you need to. Okay, so the square root of 25 is 5, the square root of 49 is 7, the square root of 100 is 10, because when you square those things, you get that number. The second type of problem on our sheet, or on the Desmos thing, was the square root of 24. So I try to explain there's two major ways of doing these problems. To simplify, that means, first of all, you can't just put a square root of 24 in a calculator or a computer and get an answer, because you're going to get something irrational. It's going to be a decimal that never repeats and never ends. So what we'd like to do is we'd like to have to factor out all perfect square factors of 24. And that's part of one of the two rules we need for rationalizing, and that would be no perfect square factors under the radical. So the square root of 24, if I look at my list of perfect squares like 4, 9, 16, 25, 36, and so forth, the only number that goes into there is 4. So I'm going to rewrite this as the square root of 4 times the square root of 6, because the square root of 4, just like problem 1, is 2. So the answer is 2 times square root of 6. Another way of doing the same problem is to do prime factors and see what happens with 24. So for instance, you could divide out 24 and say, oh, that's 2 times 12. And this is 2 times 6. And this is 2 times 3. And then we look through and we look for pairs of factors. So pairs, double roots, they're called. So the square root of 2 times square root of 2 is a double root. There's square root of 2 times square root of 2 is the square root of 4, which is 2. So this square root of 2 times square root of 2 in red, that's 2 on the outside, because that's the same as the square root of 4. And the square root of 2 times the square root of 3 is the square root of 6, because we're multiplying things on the inside with the insides, things on the outsides and the outsides. So that was about double roots. We're going to get to that in a second. So use this example to do something like this, the square root of 45. Take a minute and pause and get the answer to the square root of 45. So I got the answer for the square root of 45 by either changing this to 9 times 5. So we have 3 square root of 5 as an answer. Or you could break down 45 into its component parts. Like, for instance, if you did 9 times 5 and didn't recognize that as a perfect square, you'd do the same thing. You'd say, oh, it's 3 times 3 times 5. Therefore, we have a pair of 3's over here. So the 3 comes on the outside and the 5 stays on the inside. So that's a way of doing that one. It's the same either way. All right. So that was the second type of problem. The third type of problem is almost exactly the same, except this time you have a number multiplying on the outside. So if I have a number multiplying on the outside, it just multiplies the rest of the things. So for instance, my problem was 5 square root of 32. And the way I might do that is look for perfect squares that go into 32. Like for instance, the 5 is still on the outside, but 16 goes into 32. That's the largest perfect square that goes into 32. So I could say, well, 5 is already on the outside. Square root of 16 is 4. And therefore, we would do 5 times 4 on the outside, which is 20, square root of 2. Now, it's possible that you might have done this problem, but maybe not gotten the largest perfect square. So for instance, if you broke this down to 4 times 8, because 4 is a perfect square, you might have had 5 times 2 on the outside and 8 on the inside. But you're not quite done, because you have to test out, see if the number that you left on the inside still has a perfect square in it. Yeah, it does. This is 5 times 2 on the outside. That's 10. But since 4 goes into 8, we can say, oh, that's 10 times 2 times square root of 2. So it's still 20 square root of 2, right? Okay, so try that. I'm going to give you a problem similar to that. Let's say something like about 7 times the square root of, I don't know, let's pick a number, 28. Pause and make sure you can do this problem. All right, let's see. 28, there's a 4 in there, so 4 times 7 is 28. Square root of 4 is 2. Therefore, my answer is 14 square root of 7. I hope that's what you got also. And the next problems that we had, it was this, square root of 5 times the square root of 5. The square root of 5 times the square root of 5 is 5. Not with a radical. It's the square root of 5 times square root of 5 is the square root of 25, which of course is just 5. It's because that's the same as the square root of 5 squared. You see, the square root undoes the square. So it kind of undoes it and it becomes magically 5. Because you're asking yourself, what times itself is equal to this thing? So square root of 5 times square root of 5 is 5. If it was the square root of 7 times the square root of 7, it would be 7. If it was the square root of 102 times the square root of 102, you don't even know what 102 times 102 is to know that the answer is 102. We'll get another problem like this, but I'm hoping that you don't need to see that one. Where that's useful is in the next type of problem that I had on the diagnostic, and that was the square root of 6 times the square root of 18. The reason why this problem over here is helpful is because if you notice, you could multiply 6 and 18 together and then look and see what kind of perfect square it has in it. Or you could pull the 9 out of the 18 as well. That's fine too, but it won't give you a final answer. But if you notice that 6 and 18 both have a factor of 6 in it, they have a least common or a greatest common factor of 6. So if I instead change to this type of situation, 18 is 6 times 3, then I can see that I've got 6 on the outside and 3 on the inside for the same reason why square root of 5 times square root of 5 is 5. If you didn't do it that way, you'll still end up with the right answer. Like I mentioned before, if you said, well, that's 9 times 2 is 18. The square root of 6 is still here. So the square root of 9 is 3 on the outside, and 6 times 2 is 12. Well, is this the same as that? Sure it is. If you pull a 4 out of there, because 4 goes into 12, it's just like it's not finished, okay? So it would still be the same thing, except the way I showed first ended up having fewer steps. So let's try a problem like that, where you might want to pull out a common number, all right? So for instance, if I have square root of 14 times the square root of something else, maybe something else that doesn't have, okay, there we go. Pause for a second and see if you can see what comes out of that. Well, instead of multiplying 14 times 22, which is some large number, I'm going to divide these both because I see they have a common factor of 2. So this one is 7 times 2, and this one is 2 times 11. Now, I can take square root of 2 times square root of 2, which is the same as a 2 on the outside. Square root of 7 times square root of 11 have nothing in common, so I can just say that's 2 square root of 77, and I hope that's what you got.